Say we have a boundary between two materials here. Here's a normal line right there. Let's say we've got an index of refraction that is low here. Maybe it's air, 1.0. That's the easy one to do, right? Because it's 1.00. Here we've got an index of refraction that's higher. Maybe it's glass, maybe it's water, maybe it's diamond. It doesn't really matter. Let's say we've got a ray of light that's, let's change it up a little bit and have it coming in from the other side this time. Okay, coming in from this side. We're going to label this theta 1. Tell me what's going to happen to the speed of this light as it's going from medium 1 to medium 2, the low index of refraction to the high index of refraction. It's going to slow down, right? We're going from a low to a high index of refraction. The index of refraction is increasing. The speed is going to decrease. What else is going to decrease as a result of that speed decreasing? There's a couple of things. The angle is going to decrease. The wavelength is also going to decrease. Yeah. What's going to stay the same? The frequency, right? So if the angle is going to decrease, it's going to bend toward the normal line. In other words, theta 2 will be smaller than theta 1. Are we ever going to get total internal reflection happening here? No. You have to have theta 2 bigger than theta 1 if you want total internal reflection to happen. Now, it doesn't always happen even when that condition is met. If theta 2 can be bigger than theta 1 and still not reflect. But if you want reflection to happen, you have to have at least theta 2 bigger than theta 1. So let's switch it around. Instead of going from a low index of refraction to a high index of refraction, let's go from a high index of refraction to a low index of refraction. Let's call this theta 1 this time. So we're going from below as opposed to from above, but that doesn't really matter, right? We're still going from a high to a low index of refraction. What's going to happen when the light goes from the high to the low index of refraction to the speed? It's going to speed up, yeah. If it speeds up, what else is also going to increase besides the speed? The angle and the wavelength, right? If the angle increases, then obviously theta 2 is going to be bigger than theta 1. That's still not total internal reflection, but maybe right now you can see how total internal reflection could happen. Let's increase the angle of incidence a little bit. Theta 1 is now a bigger angle than it was before. Theta 2 is going to be bigger than theta 1 and bigger than theta 2 was before. In fact, if theta 1 is big enough, then theta 2 might actually be 90 degrees. That's the beginning of total internal reflection. That's when it begins to occur. What's another name that we call theta 1 there? The point at which theta 2 becomes 90 degrees. The critical angle, right. Anything below that critical angle, you can see theta 1 in green there, total internal reflection doesn't happen. Theta 2 is still bigger than theta 1, but it still refracts. Anything above that critical angle, and we're going to find that reflection takes place. The angle of incidence, we'll call that theta 1, equals the angle of reflection, we'll call that theta 2. Now, if we want to find the critical angle, which is exactly what we wanted to do for our questions on 673 that we had for homework, we're going to use Snell's law. Sine theta 1 over sine theta 2 equals n2 over n1. Now, technically, you could also use v1 over v2 or lambda 1 over lambda 2, but you almost always, if not always, are going to use the part of it that says n2 over n1. So you want to find the critical angle here now? How do we differentiate this from the questions that we did prior to yesterday? In other words, what special thing do we need to do to this equation to find the critical angle? Good. Theta 2 is equal to 90 degrees, so it becomes sine theta 1 over sine 90 degrees is equal to n2 over n1. We're going to rename theta 1 theta c, the angle at which total internal reflection begins to occur. What's sine 90? Sine 90 is 1, so a lot of times we might even just leave that off and say sine theta 2 or sine theta c is equal to n2 over n1. Now, some of you, I think, noticed this yesterday. When you plug your numbers into this equation, sometimes you get an error on your calculator. Anybody find that yesterday? Nobody? Oh, good for you guys. If you do get an error on your calculator, what do you think you've done wrong? You switch those around. You get those mixed up. That's the great thing about this. You almost can't mess up on this. Because if you do mess up, your calculator is going to tell you that you messed up. It's not going to give you a wrong answer. It's going to give you literally an error. And you're going to know that you messed up. You flip them over, and you're just going to switch them around and do it again. Okay? All right. Do you want to do one of these questions? Are we okay with it? Let's pick one of them, okay? Which one do you want to do? See? Diamond and water. Yeah, it's a good one. Diamond and water, because usually we're dealing with air as one of our mediums, right? Here we're not. So let's do diamond and water. Water has an index of refraction of 1.33. Diamond has an index of refraction of 2.42. Which way are we going? From water to diamond, or diamond to air? Diamond to water, I should say. Diamond to water. We know it has to be diamond to water because it's got to be high to low index of refraction. Okay, in the end, if you forget that, you mess that up, it's not the end of the world because your calculator will tell you that you've messed up. But let's try to get it right the first time here. We're going to say sine theta c is equal to n2 over n1. We could say over sine 90, but same thing. Theta c is equal to the inverse sine of n2, which is 1.33, over n1, which is 2.42. When we do the math on that one, we should get 33.3 degrees. What did you notice about these three answers here? The index of refraction of water was 1.33, 1.00, 2.42, 1.00, 2.42, and 1.33. When do you get the lowest critical angle? When there's the biggest change in index of refraction. Yeah, when you get a biggest difference in index of refraction between the two materials, that's when you get the lowest critical angle. And we talked about the whole diamond thing yesterday, right? That's why diamonds sparkle so much. That's why we get so much total internal reflection taking place inside diamonds, is because there's such a difference in the index of refraction between diamond and air. If you put a diamond in water, would you get as much sparkling taking place? No. Some sparkling would still take place. You'd still get some total internal reflection. But if you're going diamond and water, the critical angle is bigger. That means less of the rays of light are going to be above the critical angle. It's harder to exceed the critical angle when the angle is bigger. Therefore, you're going to get a little bit less reflection taking place. Okay? You guys good? We have talked about curved mirrors, and we've talked about reflection that goes along with that curved mirror, right? The law of reflection still holds. The angle of incidence equals the angle of reflection, but specifically when we deal with curved mirrors, we're not necessarily consciously thinking about that law, that the angle of incidence equals the angle of reflection. We're looking specifically at a couple of rays of light that reflect off of that mirror that obey that law of reflection, but since we know exactly what happens to those particular rays, again, we don't necessarily have to think about that law of reflection. Understand, though, the images that are formed off of curved mirrors happen because of the law of reflection. We've also talked about refraction. Refraction takes place when light goes through something and changes speed. The light therefore bends. The angle changes as a result of the speed changing. Well, today we're going to look at curved lenses. Curved lenses form certain images on screens sometimes, not on screens sometimes, that are formed because of refraction. Now, we're not going to necessarily think about Snell's law every time we do one of these problems. Again, we have very predictable rays. We know exactly what happens to a few very predictable rays. Therefore, although it's a direct result of Snell's law, we're not necessarily going to be conscious of that every time we do a problem. There are two types of lenses, just like there are two types of curved mirrors. There's convex and concave. Anybody notice a difference here, though? Convex lenses are converging lenses. Convex mirrors were diverging mirrors. Concave lenses are diverging lenses. Concave mirrors were converging mirrors. That gets a little bit confusing. Okay, we got to keep that straight. A convex lens is like a magnifying glass. Okay? It's bulged out in the middle, just like a concave mirror is bulged out in the middle. The only thing is that a convex lens causes rays that are parallel to the principal axis to converge at a focal point, whereas a convex mirror causes rays to diverge from the focal point. A concave lens, one that's thinner in the middle than at the edges. It's not like a magnifying glass. It's like the glasses on my face right now. Most people that are young or middle-aged that wear glasses have concave lenses in front of their eyes. Diverging lenses, lenses that will spread out the light because the light is not refracting and converging at the right spot. This is my eye. Okay, the rays of light are converging in front of my retina. So what do I got to do? Well, I want them to converge a little bit further back. I've got to cause those rays to spread out a little bit before they hit my eye, so that they're going to converge a little bit further back right on my retina. So I put a diverging lens in front of it. Converging lens, convex lens. Converging mirror, concave mirror. Diverging, well, it's concave for a lens, it's convex for a mirror. Last year, I think it was about a year ago, actually, I saw this picture on Twitter. This is Chris Hadfield. You guys have all heard of Chris Hadfield, probably. He was the Canadian commander of the International Space Station until early this year. And I think he had, at the peak, about 1.1 or 1.2 million followers on Twitter, which is pretty impressive. Okay, that's just a few more than I have right now on Twitter. He was great. He still is, but his tweets were especially interesting when he was on the International Space Station. If any of you guys ever saw those, it was what he'd do is he'd tweet all kinds of pictures of different places in the world and things that were happening in the world. But he'd also tweet videos of, you know, how you comb your hair in space and how you brush your teeth in space and how you go to the bathroom in space and so on and so on. All kinds of really interesting stuff that you didn't necessarily think about, that but became really, really good questions once you started actually thinking about it. This picture that you see up on the board right now, he tweeted one day, and as soon as I saw that, I thought, that is perfect. Okay, it's perfect. And right away, I put it back in these notes here. Right now, you see a bubble in front of his face, a bubble of water, literally just water in front of his face. Notice, first of all, the shape of that bubble of water. It is perfectly spherical, as opposed to teardrop shape like you'd expect a bubble of water to be. Okay. Why is it perfectly spherical? This is independent of lenses here right now, but still a good lesson. Why is it perfectly spherical? Surface tension and less force of what on it? Right. There's surface tension in water, regardless of whether you're in space or whether you're on Earth, right? But there's no gravity, or at least no apparent gravity acting on it when you're orbiting around the Earth at 400 kilometers high in the International Space Station. So it's not going to form that teardrop shape. It's going to form a perfect sphere, right? There's no other forces acting on it, essentially. The real reason that I took this picture, though, and put it in the notes here is because of the image that was formed behind there. I thought this was really cool. Okay, you see a picture of this guy, but then there's this big bubble of water in front of his face. And what do you see through that big bubble? He's upside down. And you can see both of his eyes there. So the characteristics of that image would be that it is virtual, right? We're looking through a bubble, a lens, in order to see it. It's inverted, it's upside down, and it's smaller. Okay, today we're going to draw some ray diagrams to figure out how we can predict the images that are formed by lenses, concave and convex lenses, just like we did with mirrors the other day. And then if we have time, we're going to do some mathematics with that as well. On the board right now, you see a convex lens, also known as a convex or converging. Right, if it was a mirror, it would be convex or diverging. Okay? Here we're talking about converging because the rays parallel to the principal axis don't diverge away from the focal point, they converge at the focal point. Yep. Okay. There are three rays that we can draw here, but I'm only ever going to teach you two of them because that's all we ever need to draw here. These are easier to draw than the ray diagrams for mirrors. They work out really, really well, and there's the same two that we're always going to draw. We're going to draw our object way back here first of all. That's beyond twice the focal length. Let me label a couple things actually before I do that. This is called what? It's called the principal axis. This is called a focal point. We're not going to call this one the center of curvature this time. Okay, we're going to call this just twice the focal length. It would correspond to, on a mirror, the center of curvature, but it's not actually the center of a circle for a lens. So we're going to call it twice the focal point. We've got our object beyond twice the focal point, way out there. Two rays that we're going to draw here. The first ray is from the top of the object. You can probably take a guess on that one, parallel to the principal axis. Let's draw it to the center of the lens, to the middle of the lens, not the physical center of the lens, because it's not going down here. but to the middle of the lens, parallel to the principal axis. Where do you think it goes from there? It's not going to reflect down like this, like it did for a mirror. It's not going to reflect up like this, like it did for other mirrors. It's going to refract. It's going to bend down through the focal point. Now, understand, when I draw this ray, it's a bit of a simplification. Because the reality is, the light doesn't bend once. The light bends twice. When it hits the boundary between the air and the glass, or the air and the plastic, it bends. And then when it hits the boundary on the other side between the plastic or the glass and the air, it bends again. So it actually bends twice. We're only drawing one bend, but the net effect is this. The way that it would really look would be more like this. Right? It would bend here, and then it would bend again as it left there. The final product is exactly what you see right here. If we cover up what's in the middle, then it's perfectly accurate. If we expose what's in the middle, it's not quite accurate, but it doesn't really matter because in the end, this is what we care about, the ray that comes out the other side. Second ray. Second ray is going to go from the top of the object down through a point in the center of the lens that we call the optical center. And it's going to go straight through that optical center. We'll call that the OC, the optical center. Straight through. These two rays converge on the right-hand side there, below the principal axis. My image is formed on the right-hand side. My image is smaller than my object. My image is inverted. And is my image real or virtual? My image is, no, it's real. How do you know that it's real? Solid lines intersect. It could be projected onto a screen, but we know that it could be projected onto a screen because it's solid lines that intersect. Now, if you think back to mirrors, every time we had a curved mirror and produced a real image, it was produced on the same side of the mirror as the object was. Now, every time we get a real image, it's going to be produced on the opposite side as the object. It's because the light goes through the lens instead of bouncing off the lens. Smaller, inverted, and real. Let's take a look at the next one. This time we've got our object at twice the focal length. Remember, the focal length, the real focal point is still over here. We're just using these points on the left-hand side as spacers, basically. Same two rays. First ray parallel to the principal axis, to the middle of the lens, down through the focal point. Second one is going to go down through the optical center, like this. These two rays are going to converge right over here below twice the focal length. Sometimes when you're drawing this on your diagram, it doesn't work out perfect, but it should work out perfect if you draw the lines the way you're supposed to. If it's not perfect, then fudge it a little bit so that you can see in your diagrams that this is what it's supposed to look like. Characteristics. Number one, larger, smaller, same size. Use my fingers here. Looks to be pretty close to the same size, right? Upright or inverted? Inverted. Real or virtual? It's real. It can be projected onto a screen. We know that because it's solid lines that intersect. Next one. This is a good one to go over here because there's a lot of applications to this one, a lot of real-life practical applications to this one. First ray, parallel to the principal axis, down through the focal point. Second ray, down through the optical center. Produces an image way over here where these two lines intersect. Number one, that image is clearly larger or bigger. Two, it's inverted. And three, it's real. Where do you think you see something like this? Sorry? No, not a magnifying glass, no. In a magnifying glass, you're not projecting the image onto a screen. You're looking into the magnifying glass, right? That's a virtual image. Plus, when you look into that, it's not upside down, is it? Look in a magnifying glass, it's right side up. You're looking at it, you're staring at it in the face right now, quite literally. Well, not quite that literally. You're looking at it right now. Yeah, it's like a projection system, like a movie theater or projection system that you're literally looking at right now. We've got an object inside that projector. That object is somewhere between the focal point of that and twice the focal point of that projector. That produces an image that's real. We want a real image, right? Projected onto the screen, projected onto the smartboard right now. Well, we want it to be bigger, because if we had an image that was the same size as the object inside that projector, then it wouldn't serve much purpose. What's the deal with upside down, though? Seems like the image you're looking at right now isn't upside down. Looks like it's right side up to me. Take a look at the projector. The projector is upside down. So our object is upside down here, and it flips the image over. Now, we're kind of fudging that a little bit, because you can electronically flip the object inside there. Okay, when you buy that, take it out of the box, okay, set it up on a table right side up, it'll produce an image that's right side up. We have to change a setting on that projector to make sure that we get an image right side up when the projector is upside down. What that setting does is flips the object over inside there, electronically flips the object over. So right now, the object is upside down on that projector. Okay? We always want the object to be upside down on the projector. We just have to do a little setting on the projector to make the object upside down. Okay? It produces an image that's real, that's flipped over, but that's okay, because if the object is upside down, we want it to be flipped over, and it's going to be larger, which is obviously desirable. This is a movie theater screen, right? Okay, movie theater screen. If you were to look back at the film that's going through the movie theater projector, that film would be upside down. The object would be upside down there. Next one. First ray, parallel to the principal axis, goes down through the focal point. Second ray goes down through the optical center. Where do they converge? Well, they don't on the right-hand side. Let's extend them back. Where do they converge over here? They don't. What are the characteristics? No image. Last one for our convex mirrors, or sorry, convex lenses, or our converging lenses. So we got our object, it's inside the focal point. So in other words, an object that's really close to the focal point of this lens. First ray is going to go parallel to the principal axis. It's going to go down through the focal point. Second ray goes down through the optical center. Do they converge on the right-hand side? They do not. So what am I going to do with that? Let's extend them back as dotted lines. They converge back here. Characteristics? It's larger, clearly larger. It is upright, and it is real or virtual. This one's virtual. What do you got to do in order to see this one? You got to look to the lens, look into the lens in order to see it. Where have you seen this one every day? Logan? This is our magnifying glass, right? Whenever you use a magnifying glass to see something, to magnify something, where do we put the magnifying glass? We put it close, right? We put it close to the piece of paper or to whatever it is that we're trying to magnify. Why? Because we want that object, that piece of paper or whatever it is that we're trying to magnify, to be closer than the focal length. If we pull it back, then that's not what we see. So we just intuitively put the magnifying glass close to the object. Okay, we make DO smaller than F. That produces an image, a virtual image, because we have to physically look into the lens to see it, an image that is larger, an image that is upright, and an image that's virtual. Well, we have one more type of lens. We've gone through 5 ray diagrams for convex lenses, for converging lenses, and I think you find probably that the ray diagrams are a little bit easier than they were for converging mirrors. I find that they are anyways. The 5 ray diagrams that we use for diverging lenses or concave lenses are also at least just as easy as they are for diverging mirrors. First ray is going to go from the top of the object parallel to the principal axis. Again, it's actually going to bend twice, not once, the way that I'm drawing it here, but the net effect is the same. Where do you think that ray is going to go now? Down here? No, that would make it a mirror. If that was a concave mirror, that's what it would look like, but it's not. It's not going to go up here. It's not a mirror at all, so it's not going to reflect. It's not going to go down here because that would be a convex lens. Where do you think it's going to go? Good. As if it's originating from the focal point. This is the first one closest to the lens. There's the focal point. So it's going away from that focal point. The second ray, exactly the same as it was for the last set of ray diagrams. Top of the object, let's put that back. This one's going to go from the top of the object down through the optical center, and it's just going to keep going through the optical center. Now, they don't intersect anywhere on the right-hand side, so let's extend them. This one gets extended back to the focal point. Do they intersect now? Yeah, it looks like they do. But we have a solid line and a dotted line intersecting. Is that real or virtual? Well, we don't really have a solid line and a dotted line intersecting. We always look for either 2 solids or 2 dotted lines that intersect here. If we extend this second ray back along itself, like this, then you can see that 2 dotted lines still intersect, right? Now we know for sure that this is a what kind of image? We know for sure it's a virtual image now because it's 2 dotted lines that intersect. You know what? I'll be honest with you guys. Most times I draw this, I don't even draw the second ray back because I know where it's going to be, right? I know it's going to intersect in the same place. Technically, it should be a dotted line that goes backwards, though. My image is formed right there. That image is smaller. That image is, it is upright. And that image is virtual because, again, it's dotted lines that intersect. I'm nearsighted. That means that I can see things close to me, but I can't see things far away. That means that the rays of light that are coming through the convex lens in my eye converge in front of my retina. I still get an image that's formed on my retina, but it's not a focused image. I would need to move my retina forward in order to get a focused image on my retina. Well, I can't really move my retina forward. Okay, that's not practical to do. So what's the alternative? If the rays are converging too soon, let's use a concave lens or a diverging lens to spread those rays out before they hit my eye. So let's put some concave lenses in front of my eye, in front of my eyes, to cause the rays to spread out. That way they're going to converge a little bit further back on my retina. As I get older, and as you get older, nearly all of us, if not every single one of us, assuming we live long enough, we will need reading glasses. Okay, we will need reading glasses. The muscles in your eyes weaken as you get older. Reading glasses are convex. Reading glasses are like magnifying glasses. That's so you can see things that are nearby. You need those because the rays of light that come through your eye at that point converge behind your retina, too far back. So what do we got to do? Not spread the rays out before they enter your eye. We got to bring them together before they come into your eye. Make sense? If you're ever on Survivor and you ever want to start fire on that first day of Survivor, what kind of glasses do you need? Do you need regular glasses like most of us have right now, or do you need reading glasses? You need reading glasses because you need the rays to converge at one spot, not spread apart, right? Okay, finish the rest of those ray diagrams up for the weekend, guys. Okay, they're all going to be the same, so don't think it should be a problem. If you have any trouble with it, let me know on Monday, all right? Have a good weekend, everyone, and we'll see you on Monday.